Yes, I was maybe a little bit aggressive with respect to Tim Maudlin, because I said that this year is 450 years of the birth of Galileo. And so if that would be very nice if we could have some lectures related to the question of relativity and Galilean relativity, which is one of the highest achievements of humankind. So I think that will be a nice introduction, and there will be a lot of discussion around these notions. So please, Professor Maudlin, can you give your lecture?
Thank you. So, right, so that's why this talk is what it is. I've never given this talk before, so I'm not quite sure how. I may be done very quickly, and then we'll just sit around and look at each other. As it turns out, and it's maybe also an appropriate talk for this kind of venue, because the concepts in the title are physical, clearly, but both of them, I think, are not entirely clear, or at least subject to a lot of dispute. And so I want to tell you a story about the connection between these. And also, I'll talk a little bit about the individual disputes. So what I mean in the case of Galilean relativity, if you're a physics student or a physicist, you think, well, of course, this is just some kind of true principle about the actual world. Right? It's telling us something about the world, and maybe something, what's involved, what's the subject matter? Is it just about the structure of space and time? Is it about dynamical laws? Is it about something about the physical contents of the world? And so exactly what Galilean relativity is if you start scratching the surface, not entirely clear. There's a bit of a literature in the philosophical literature of people with different views. And if I think of it, I'll mention some of the things people say about trying to make sense of just even what the principle is. And then there's a dispute about the Lorentz contraction. So again, if you have studied relativity, you've heard about the Lorentz contraction. But you're, I guess, as likely to have heard that that was a mistake, right? That early on, in trying to explain certain experimental results, in particular the results of Michelson and Morley or other attempts to experimentally verify the motion of the Earth through the luminiferous ether, that the null results of those experiments, in order to come to terms with them, at some point Lorentz and Fitzgerald had proposed a physical effect called the Lorentz-Fitzgerald contraction. And my guess is that if you look through books or you just ask random physicists, you're as likely to hear that that was a mistake, that, as it were, from a modern, deep understanding of space-time theory, there is no such thing as a Lorentz-Fitzgerald contraction, right? That was a kind of an error that was forced on the physics community by attempting to keep hold of classical physics in a relativistic context. I'm going to argue otherwise. There's nothing at all original in what I'm presenting about this, and I'll just be actually following, as you'll see, the presentation of John Bell at a certain point. But it's amazing, I think, that both of these topics, which you'd think of are just very uncontroversial central topics or in physics, I think you'll find there is dispute about them. And I'm going to at least tell you a story about what they are and how they're related to each other. And in a kind of pleasing way, because it is the 450th anniversary of Galileo's birth, I'm going to argue that Galileo got it right. Right? Galileo was right about Galilean relativity. And that more modern presentations that drift away from what Galileo actually described miss some of what's important that's going on. So we'll see how it goes. All right, so that's our first question. What is Galilean relativity. The same principle is sometimes called the equivalence of all inertial frames. And again, you'll hear that that's a fundamental principle of physics. But if you stop for a minute and ask what in the world an inertial frame is, that's also not so clear. It's the sort of thing that you have to think hard about to get a proper definition. Now, let me just give you some reasons to worry. So as I say, this is can be sort of obscure. Let me give you some reasons to worry about this, because you might say, oh, this is, philosophers, again, causing trouble. Everybody really knows what's going on. Why do we have to worry about it? So let me at least give you some reasons to worry a little bit about this. So here's one worry that you might have. It's easy to read that when you first learn special relativity, that special relativity is a logical consequence, can be derived in some sense from two principles. One of them is this Galilean relativity, or the equivalence of all inertial frames. Okay? And the other principle is the constancy of the speed of light. Okay? So it should be that if you have those two principles in place, special relativity follows. Which sounds, when you're first learning relativity, that's great in a certain sense, because you say, gee, that we already knew since Galileo that Galilean relativity was somehow a correct physical principle. All we now add is the constancy of the speed of light, and somehow, by thinking hard, from those two put together in the right way, we can actually derive special relativity. Now, why should you be worried about that? That sounds great, but if that's right, since special relativity isn't general relativity, right? They're different theories. It must be, if this is correct, that general relativity has to reject one or the other of these principles, right? And then you might sort of stop a minute and ask which one. Because we think, ultimately, general relativity is more correct than special relativity. And so now you might worry. You'd say, well, gee, when I go and learn general relativity, am I rejecting the constancy of the speed of light, or am I rejecting Galilean relativity? And you might be a little upset to reject either of them, because you have the impression that they're both very well deep-founded physical principles. Now, the other possibility, of course, is that actually special relativity doesn't follow from these two together. Which, now you've, just to see, now you've flipped everything over on the other side. On the one hand, you thought, oh, gee, it would be great if special relativity followed from these two, because these two are very clear physical principles. But now you say, well, it would be much better if special relativity didn't follow from the two of them, because then I would have a hope of saying, even in general relativity, both of these still obtain, right? So I just want to make you uncomfortable in the beginning. Okay. So hopefully this will start to get you a little bit worried about why we should be concerned about getting clear about all this stuff. Okay. So if you followed that again, you'd say I have to reject either this or that. Well, which one? Which one goes in general relativity? Yeah. Well, that's an interesting.
You generalize the notion of how many transformations you allow in your set.
Right, but if that were the right story, you see, that wouldn't solve our problem. Because, you see, if the Galilean, wait, let me finish the response. If the Galilean transformations are just a subset of a wider class of transformations that are respected in general relativity, then, of course, if they're respected in general relativity, then the smaller subclass is also respected, right? Yes, if a smaller class, if a larger class is respected, a small subpart of it is respected. So, can I finish? Wait. No, can I finish speaking, please, before you interrupt me? if you have a wider class of transformations that are all respected, every subclass of that transformations is respected. That's just logic. Okay, that's just logic. So if Galilean relativity is respecting a subclass of those transformations, then it is respected in a theory that also respects a wider class of transformations. And now we're back in the problem again. So we just have to think a little hard. Again, now we have to ask what an inertial system is or what an inertial frame is. These are the problems I'm trying to raise. Here's another thing you might be concerned about. Exactly what we're talking about. If the principle is the equivalence of all inertial frames, the question is, what is an inertial frame? Now, there's going to be one way, I guess, I don't know, I hadn't planned to talk about this. Maybe I will come back to this in the end. There's a sense in which you might say, well, gee, actually, in general relativity, in general, there are no inertial frames. They don't, globally, they don't exist. Okay? So there just are none. Well, they're all equivalent in a trivial sense if there aren't any, but that's not an interesting physical principle. But if that's the principle, if the principle of Galilean relativity is the equivalence of all inertial frames and there are no inertial frames, then Galilean relativity doesn't hold general relativity. But I thought it was a really important physical principle, right? Okay? So that doesn't look too promising either. And furthermore, when you say all the frames are equivalent, it's not entirely clear what kind of equivalence you have in mind here. In particular, is it just phenomenological equivalence, equivalence with respect to the observable phenomena, or is it equivalence in some deeper sense than that? And that'll make a big difference to how we understand the principle. Is it a restraint entirely on the observational data, the phenomenology, or is it some kind of deeper principle that's going to constrain even not directly observable facts? Okay. So let me give you an example of a case where you could say Galilean relativity holds, but it's not, it's merely at the phenomenal, in a certain sense, merely at the phenomenological level. Look at Newtonian mechanics. If there was one theory that is supposed to satisfy the constraint of Galilean relativity, it should be Newtonian mechanics. But think about Newtonian mechanics in the way Newton thought about it. So Newton believed that there was an absolute space that persisted through time, and with respect to that absolute space, you could define absolute velocities. There was a particular state of absolute rest, which would be an object remaining in the same part of absolute space through time. So in that sense, now Newton proves, this is corollary 4, we'll be talking, corollary 5, I'll be talking about two of the corollaries that are corollaries to the laws of motion that Newton proves early in the Principia. So corollary 5 is the one where he proves what's normally thought to be Galilean relativity from the fundamental principles of Newtonian mechanics. It's not quite accurate that what he proves is that it follows from the laws F equals ma, as it were, alone. It doesn't. But if you're looking at impact forces and the assumption is that the impact forces only depend upon the relative velocities with which things collide with each other, then Newton proves that the relative motions, the motions among themselves, right, with reference to each other of a set of bodies, will be the same whether that entire system is, as it were, at rest in absolute space or the entire system is moving uniformly through absolute space. So that's Newton's version of Galilean. And he actually mentions, by the way, Galileo right after this in the text. So he knew that too. But of course, for Newton, if you think of these different inertial frames, as it were, they're not all equivalent. They're not all physically equivalent. The absolute rest frame is really special and important conceptually for Newton. So if you think that Newton was able to prove some kind of Galilean relativity from his principles, then you're thinking of it as a statement just about the phenomenology, by which I mean what Newton says is what's really observable, right? What directly falls under the survey of our senses are the relative positions and the relative motions of objects. Even though he absolutely had to have absolute motions to write down the laws of physics, he's perfectly aware that you can't observe absolute motions, that all you can observe are relative motions. And what he shows in the corollary is that the relative motions will be invariant in these two cases. So you could say it's really a statement about the phenomenology, and you shouldn't take it to be anything deeper than that. Now, the normal approach, modern approach, I think, to Galilean relativity is to relate it, which is sort of what we were talking about a minute ago, to symmetry principles. And in particular, to say that Galilean relativity is really a statement of the existence of a certain kind of space-time symmetry. That, of course, is not yet to tell me exactly what it is. And that symmetry is symmetry under an operation, under a mathematical operation that's often called a boost. And if there's another word we're going to think about to death, is the word boost here. Right, that's why I'm putting it in quotation marks, just to keep it in your mind. There is, what I mean by a boost here is just a mapping, okay, a global mapping of the space-time onto itself, a global mapping of the space-time onto itself. And you can ask whether various aspects of the space-time structure are unchanged under that mapping, in which case it constitutes a kind of symmetry. Now, what's nice about this at a very high level, this is at a kind of high level of abstraction, because I haven't told you exactly what the space-time symmetry is. And you might say, well, gee, there is such a space-time symmetry in the Newtonian theory with absolute space and time. There is a similar, or maybe in some sense, I'm not sure, you would say identical symmetry in what we call neo-Newtonian space-time, which is a space-time that does not have absolute space and therefore does not have any absolute motions. And even in Minkowski space-time, which has a very different geometrical structure, that structure could still display a certain kind of global symmetry that we would think is the way Galilean relativity manifests itself in that setting. Now, these obviously can't be literally identically the same symmetry, because the geometrical structure of Minkowski spacetime is very different than the geometrical structure of either of those two. The geometrical structure of neo-Newtonian spacetime is, as it were, a part of the geometrical structure of Newtonian absolute space. So there it could literally be the same symmetry, the same transformation. But you would then need a kind of abstract characterization of what this symmetry is that it would apply in these rather different geometrical settings. So that looks like a fairly promising way to go. Let's look at the symmetries, in particular certain global symmetries of the space-time. Maybe that's all there is to Galilean relativity. So if we go back again to Newton's case, if Galilean relativity is supposed to be some kind of boost symmetry, then in absolute Newtonian space-time, that's not a complete symmetry. That is, the entire structure, the entire geometrical structure isn't preserved under that symmetry, exactly because the absolute velocities of things would change when you, as it were, have them. The symmetry would somehow be associated in Newton's mind, as he would even say it is. Imagine I do an experiment in a laboratory that's at absolute rest. And then I do what's in a certain sense the same experiment, and a lot of what we're going to be talking about is just what that means. I do the same experiment in a laboratory that's in uniform absolute motion. What you can think is that what corollary 5, what Newton proves, is that under certain restrictions on the sorts of forces that are at play in those experiments, he can show that in a certain sense the observable outcomes of the experiments will be the same. That is, the relative motions of the particles will be the same, and since that's all we can see. But notice, he would say these are still different situations. I mean, these are interestingly physically different situations. One's at absolute rest and the other's in absolute motion. So this is not, as it were, a symmetry of the entire physical situation. It's just a symmetry of the phenomenology. Okay? But in order for that to be true, of what follows is that no mechanical experiment can reveal the absolute velocity of an object. Because if it could, then obviously the outcome of such an experiment should be different in the laboratory at absolute rest than the laboratory in absolute uniform motion, right? Your absolute velocity meter ought to register differently in those two situations. So in the case of Newtonian absolute space and time, because the symmetry is only a symmetry of a part, not all of the space-time structure, if it yields this phenomenological equivalence, it means that part of that structure, the absolute velocities, are not observable. And at that point, what you're tempted to do is say, look, if these absolute velocities are not observable, if I can actually prove from fundamental physical principles that the absolute velocities have no observable effects, wouldn't it be better to get rid of them altogether? Doesn't that mean that in some sense postulating these absolute velocities is physically idle? It's not doing any real physical work. Shouldn't I try to modify the theory in some way to eliminate the absolute velocities? Now, as it turns out, just again, 2 points here. One is that as a methodological principle, that seems quite sound. That you should be motivated if by analysis of the physics you can prove that something postulated by the physical theory will, according to the physical theory itself, not be observable. That should motivate you to ask the question, can I get rid of that unobservable structure? Now, as it turns out, in the case of Newtonian absolute space and time, once you're fancy enough to think in terms of space-time, and really this wasn't done until after relativity, that people understood, got used to thinking of space-time structure so they could even do this. Once you write out Newton's picture of space-time structure in terms of space and time, it's fairly clear that you can, as it were, in a very surgical way, cut out the bit that allows you to define absolute velocities and keep everything else. I mean, it's really just a case of directly subtracting a piece of space-time structure out. Essentially, the piece of space-time structure that would identify individual points of space through time. Okay, so it's sometimes called a rigging mathematically. It doesn't matter. It's just the fact is you can just take that piece, that mathematical piece, and literally erase it and leave everything else. And you then end up with a theory that makes all the same predictions in terms of the observable phenomena, that is, the relative motions of things, as the original theory, but doesn't have this extra piece, unobservable piece to it. Okay, so that's a tremendous success for that methodological idea. I just want to register here, there's no proof that you can always do this. That is, there's no principle that tells you if, according to the physics itself, there's an unobservable piece of the structure that you use to write down the physical theory, that there's going to be any way, much less an easy way, to modify the theory to just pull that piece out. All right? You might think there ought to be. You might hope there is. You might look for it. It might not be there. And although this goes far beyond anything I'm going to talk about today, that essentially is what's going on when you worry about non-locality and sort of an absolute foliation of space-time in trying to understand non-locality. You can write down theories that postulate a kind of absolute foliation of the space-time. So people often compare this to Newtonian absolute time, as if you're reintroducing it. It's not quite exactly the same thing, but you're reintroducing something like Newtonian absolute time back into the picture. You write down a theory using that to specify the dynamics of the theory. You analyze the dynamics and find that if the dynamics is correct, no experiment can reveal this structure. That would again motivate you to ask, can I pull it out again? Right? Can I somehow erase it? But the answer might very well be, and in certain cases clearly is no, not in any obvious way. It's too deeply entwined in the physics to then simply be extractable. You're really using it in the physics. And you may end up in a situation where you have a physics which implies the unobservability of one of its essential elements. Now, again, this is a point where physics and philosophy have met in the past and meet over and over again. So in the time of the logical positivists or the logical empiricists, they adopted a theory of meaning which would have said, well, if you try to postulate something that has no observable consequence, that you can't observe, let me put it that way, not has no observable consequence, that you can't observe, what you've postulated is literally meaningless, right? Because the very meanings of the words we use have to be articulated via observable consequences of hypotheses. And then they would say, what you're doing is kind of incoherent. That was bad philosophy. It was bad philosophy of language. It was sort of a big mistake. It happened to be a mistake that was motivated by people learning about relativity. It takes a while to get over that.
May I
Yeah.
just interrupt you? If I look at these sentences and if I don't think about relativity,
Yeah.
but only in general physics, but whatever is not invariant under the system. For example, parity correlation. I mean, we have the symmetry of the parity symmetry for the forces. And this symmetry is broken by weak interactions.
Yes.
But it's observable.
Yes.
The effect is observable.
Yes.
Because it cannot be observable. Okay, observable effect.
No, I mean, this is a case.
If I set aside relativity.
This is, I mean, the point is, parity is not a symmetry. The symmetry is broken. That's the opposite case. That's the case where everybody thought there was a fundamental symmetry in the basic ontology, in the basic physical, what you're postulating physically, right? They thought that for all physical purposes, right-handed and left-handed should be equivalent, right? There shouldn't be a physical difference between them. There should be a perfect symmetry of all the physics under that transformation. That turned out to be false and observably false, as you said. You can actually do experiments that phenomenologically break the symmetry. So this is the opposite case, right? This is the case where, in the case of Newton, with absolute velocity, you would break the symmetry at the theoretical level, but it wouldn't be broken at the phenomenological level. The case of parity is the other way around. It's one where you thought you wanted it at the theoretical level, at the foundational level, but it turned out to be broken at the phenomenological level, which told you you better break it at the theoretical level. Right? If the actual phenomena don't obey the symmetry, then of course the fundamental physics can't obey the symmetry.
But I also have a little bit problems with the absolute velocity. I mean, velocity of light is absolute velocity.
Well, yes, so that's...
You can in fact measure velocity, your velocity with respect to light. You know, it's frequency shift.
Well, you see, so that's an interesting observation. Again, let me just point that out. I mean, I agree with you, it's puzzling. So here's a puzzle. According to Newton, every object had an absolute velocity. There's a fact about how fast we are now traveling through absolute space, in what direction, okay, according to Newton. It was a fact which, again, he proves in Corollary 5 under certain restrictions on the dynamics. On the forces, it's a fact that you could not do an experiment to determine what our absolute velocity is, but for Newton, it is an actual physical fact. Okay? When people, because you couldn't observe it, people thought, well, it's great that I can actually reformulate Newtonian mechanics in a different setting, in this neo-Newtonian space-time or Galilean space-time, where there is no such fact. And furthermore, what people would normally say is right now, if you ask, what is my velocity? What is my velocity right now? What is our velocity? We don't have one. It's just there isn't an answer to that question. Now, it's a bit hard to take that in because 90% of the time, people also talk as if we do. So you hear people say, you know, what would things be like if we were going 99% the speed of light? Well, we are going 99% the speed of light. Or anyway, there's a perfectly good inertial frame, as good as any other inertial frame, according to which we are right now going 99.9999999% the speed of light. There's another perfectly good inertial frame. Again, now I'm not, you know, this is just the way you would speak, another perfectly good inertial frame, as good as the first one, in which our velocity is now 0. Okay? Now, if you say both of those are perfectly good, neither one is right, physically right or wrong, then you say there's no fact at all about what our present velocity is. Now, you're right. What's often said is, so you say, look, there's no fact about how fast we're moving. There's no fact at all about how fast we're moving. But there is one object in the universe about which there's a fact of how fast it's moving, namely light. Now, that sounds strange, doesn't it? I mean, you know, that ought to strike you as a very odd thing to say. How could it be that no massive object has an absolute velocity, but light has an absolute velocity? You would think that if there were the resources to define the absolute velocity of anything, there would be the resources to define the absolute velocity of everything. So again, there's a kind of a puzzle there. I'll actually talk at the end here what we mean by saying the speed of light is constant without that you can make physical sense. I mean, that's actually the end of this talk. What physical content does it have to say that the speed of light is constant if there are no speeds? If fundamentally there are no speeds of anything? Again, you might say, well, that's just self-contradictory, right? How could you say the speed of light is constant and furthermore nothing has a speed? Well, I'll talk at the end of this talk about physically experiments, how that could be, as it were, unpacked in terms of phenomenological, the results of certain kinds of experiments. So we'll come to that. Right, so as I said, Newton, only the relative distances are observable, and he's very clear about this. I mean, Newton is just so admirably clear about all of this. If you haven't read the Principia, at least read the beginning of it. That what we can observe are just relative velocities and relative distances, and therefore relative velocities, and therefore the observable phenomena are preserved under this symmetry. Now, so what is this boost symmetry? I've been talking about this symmetry of space-time. Now, in the classical case, so these are just pictures relating. I mean, you could actually think of this, if you want, the easy way to think about these two is in Newtonian absolute space, although it'll be fine even if you get rid of that. But these, as it were, represent two different worlds, two different ways that matter could be distributed in the world. And these slices represent moments of Newtonian absolute time. What these represent are what Newton talks about when he's arguing for the necessity of believing in absolute velocities, right? Why did Newton believe in absolute space and time? Well, because he said, one thing I can observe is absolute acceleration. I can tell when an object is accelerating. And I can tell in a way that has nothing to do with its changing relative position with respect to any observable body. And the example I mean, this goes back to Newton's discussion of the rotating bucket. He says, I can tell when the bucket is spinning because the water, forms a concave surface when the bucket is full of water is spinning. And he goes on later at the end of his scholium to say, imagine a universe with nothing in it at all except two spheres tied together by a cord. So there's nothing to compare their relative positions to except each other. And suppose their relative positions with respect to each other don't change. So there is no relative motion at all. There's no sphere of fixed stars. There's nothing. There's just this big vacuum with these two objects in this cord. He says, still, I can tell experimentally, observationally, whether that system is rotating or not. Because the cord connecting these two things will either have a tension in it or it won't. And the tension could be of different magnitudes. So this corresponds to my system of two spheres and the cord where there's no tension in the cord. And the whole thing is just, as it were, sitting there quietly in absolute space. And the trajectories are inertial trajectories. And this is the case where the two spheres are rotating around their common center of mass. And we see that their trajectories are not straight. They're not inertial trajectories. In order to produce the curvature of these trajectories, you need a force. And the force is going to be provided by tension, observable tension, in this cord connecting them. OK, so this represents a world with two of these two-sphere systems, one of which isn't rotating and one is. And then a classical boost takes you from this situation to this situation, where, again, there's no tension here, but as it were, this system, instead of, if you want to think of this in absolute space, instead of being at rest in absolute space, is now just drifting at a constant velocity through absolute space. And my rotating system is still rotating, and the tension is exactly the same. But that system, too, is now also drifting. In addition to its rotational motion, has this constant drift. OK? Now, this is a symmetry transformation because if this is a solution to the dynamical laws, this is a possible physical situation. This also is a possible physical situation. Right? That's what it is to prove that this is a symmetry under the dynamics. OK, so that's what you normally mean. And again, I wanted to worry about boost. Normally, what you mean by a classical boost is a mapping on space-time that, as it were, if I send the matter along the map, it would take me from this situation to this situation. What about a relativistic boost? Well, a relativistic boost, and we're going to come back to this, it's the same sort of thing. You have to think of these as it were, two separated worlds or two separated possible physical situations in the same world. Here's a bunch of matter. This is in a relativistic setting, so there's a light cone structure. There's a light ray traveling along a light cone. And I've got a bunch of matter that's obeying whatever dynamical laws they obey. And then under a Lorentz transformation, now I can map this space-time onto itself in a way that preserves the metrical structure and alter the distribution of matter in accordance with that and get this situation. And again, under very general restraints on the dynamics, it's provable that if this is physically possible, then this is physically possible. They're both going to solve, right? If one solves the equations of motion, the other does as well. These are, again, global transformations. You send the entire space-time onto itself, okay, in accordance with what we would call a Galilean transformation or a Lorentz transformation. So that's often what people think of as a boost. I hope this is familiar. We're going to see for a minute. This isn't what Galileo had in mind. Okay? So just to keep track of where we are, Galileo's still sitting out there. This is not what Galileo had in mind. So insofar as you're thinking in these terms, you're drifting off of the original inspiration of Galileo's observations. And you have to bear that in mind to see where a lot of these conceptual problems arise. OK. Now, suppose we have these transformations. So transformation is just a mapping from the space-time onto itself. I can, again, carry matter fields or whatever along the mapping. Now, one thing that people often observe is that these kinds of mappings, mathematically, what looks like the same thing, I would write down literally identical mathematical equations. These transformations have two different physical interpretations, active and passive. So again, I hope this is familiar, but it's worthwhile, again, to think through, because I think this is the source of a lot of conceptual confusions. So you've got the Lorentz transformations. Think of them just mathematically. I mean, we've all seen them, right? You've got x, y, z, t, x prime, y prime, z prime, t prime, and you have some equations to tell you one set of coordinates in terms of the other. Now, what Lorentz said was he thought about thinking of these in an active way. So imagine I have a certain situation. I have these two sets. I have one space-time and two sets of coordinates on it. And these transformations give me the value of one set of coordinates in terms of the other coordinates. Now, I describe a physical situation in terms of the first set of coordinates. Right? I say, well, the matter, for example, is located at such and such points. And then I say, suppose there were a different physical situation where the matter was located elsewhere. Where? Well, the same locations in terms of their coordinate values in the second coordinate system as they have in the first. Right? So now you're, as it were, picking up the matter from one point in space-time and moving it. And what the transformations tell you is where to move it to. Okay? So that's an active transformation because it's a change. It's what you end up with are two different, physically different possible situations, which Lorentz called corresponding states. And what he shows, again, is that if the first situation obeys the laws of physics, and the laws of physics, in this case, electromagnetic theory, if the one situation obeys Maxwell's equations, then the other situation will. Okay? So if one situation is physically possible in the sense of being a solution to those equations, the other situation is. So you really have two different physical situations, and this is an active transformation because it's taking you, it's relating one physical situation to a different one. As it were, if you were to somehow be able to implement this transformation, whatever that means, because this is a global transformation, you would be changing the physical state. On the other hand, okay, so that is then what we would call an active transformation. On the other hand, there's another thing you do. You say, well, suppose I just have one physical situation, but I want to describe it with respect to two different reference frames. Then you have a passive transformation. It's not a transformation of the physics at all. You have one physical situation. Of course, the physical situation is what it is. It gets one coordinate-dependent description in one frame. It gets a different coordinate-dependent description in the other frame. That's a passive transformation. Now, there's one thing that's clear, is that whereas you need an argument that the physics doesn't change under an active transformation, you need no argument that the physics doesn't change. I mean, the phenomenon doesn't change. Let's put it that way. The observable phenomenon doesn't change under a passive transformation, because a passive transformation involves only one physical situation, right? As we'll see in a minute, we're going to try and understand a certain puzzle. A passive transformation can't produce a physical effect. It's just a coordinate change. Whether something like an active transformation can produce a physical effect, that's a different worry. Now, so if you don't, unfortunately, the mathematics looks the same. So if you're not really clear about how you're using the mathematics, what it's representing, and you just, in your mind, switch between the active and passive readings, you're going to draw certain conclusions which are perfectly accurate. You say, look, a passive transformation, that can't change the phenomenon. Therefore, an active transformation can't change the phenomenon, or something like that. And then you're going to get into a mess. OK. So if the passive and active transformations were really, in some sense, equivalent, then it's trivial to see that there can be no observable consequences from a boost. Right? A boost can't physically produce anything. Quick argument to that. Now, all of that has been trying to explain a bit of what one might mean by Galilean relativity in terms of these global symmetry principles. Is that what Galileo had in mind? Well, here's the relevant passage from Galileo. It's really quite beautiful. I won't read the whole thing, but he goes on and remember what he does. He says, I'm in a boat, I'm in a ship at anchor in a calm sea, and I do a bunch of experiments, right? I'm in the hold of the ship, I'm shut up in it, and I jump this way and that way, and I throw a ball to my friend, and I let some moths or butterflies fly around, and I let some fish swim around, and I let a thing drop water down into a bowl below. And what I notice, and he says you somehow don't even have to do this experiment to be absolutely sure this is how it's going to come out. You're sitting there at anchor, that you're not going to notice any asymmetry in directions, right? You're going to be able to jump the same distance toward the aft and toward the stern, and the butterflies are going to fly around equally in all directions, and so on. Okay? So you do that experiment, and you notice, again, this is empirics, this is phenomenology, you notice these results. And then he says, now we're going to do the second step of the experiment. Having observed them, then have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. So as we would say, an inertial motion. Take the very same ship containing the very same apparatus, the very same pieces of equipment, and accelerate it, and then stop accelerating it, okay? So this is the point I want to make. This is not a global transformation of all space-time, okay? It is an actual physical change to a particular piece of matter, or a bunch of pieces of matter, okay? So you let the ship now proceed at any speed you like, as long as the water is calm, and you repeat all of your experiments. And you notice that on the second repetition, the phenomenology is the same, right? The droplets will fall as before into the vessel beneath without dropping toward the stern, although while the drops are in the air, the ship runs many spans, and so on. I mean, notice he actually describes this the way Newton would. That is, he says, in the first case, the ship isn't moving. And in the second case, the ship is moving. So it's physically in a different situation. The drops in the one case, when they drop into the water, just drop straight down. And in the other case, the drops somehow cover a large span. So it's really a physically different situation, but phenomenologically identical. Right? The phenomenology doesn't change. So that's what Galileo meant by Galilean relativity. And my point here, yeah.
I have one thinking about one example. Well, not very, could be practical, but very difficult.
Yeah.
And because if you have a charge on your ship,
Yeah.
and you accelerate, it will radiate.
Yes.
And so because of radiation of the charge, you will notice that you are accelerating. So
That's right.
that would be measured. Then you stop.
Yes.
Immediately after that, you could say, well, I have certain speed before I can do experiment, but I will notice that the radiation hasn't disappeared. It's going away, but you could be able to measure that it's still there. So you would have information that you were accelerating, and then in fact perhaps your frame is still not yet fully inertial.
Well, this is, I mean, so look, so you're exactly right about the first point. Galileo makes no claim, and he better not, because he would be wrong, that you are not going to notice any difference in these experiments at all through the whole course of this. During the acceleration, right, as the ship goes from being at rest in the harbor and gets up to speed, the water will not drop straight down. The butterflies will congregate at the stern, okay? You will be able to jump further in one direction than the other. The phenomenology during the accelerative phase of this experiment will change. His claim is that once it's over, now you're right, there may be traces of the past acceleration. So there's never a claim that you can't tell that you're accelerating. And that again, look, that again was Newton's point. Newton's point was that I can tell when I'm accelerating. I can tell when the spheres are accelerating, right, when they're rotating. There's tensions. I can see them. I can tell when the bucket is spinning. It's observable. The observable effects are different under acceleration. Galileo's claim is not that you can't tell when you're accelerating. It's that when you stop accelerating, but you would say because of the intervening acceleration, you're now in a different state of motion.
But there is a big difference between bucket of water and radiation. Because when you stop accelerating, bucket of water, you may say, well, it will, waves will be in bucket of water. You can say, well, their motion is totally with the concept of inertial frame, etc. But not radiation. Radiation you cannot get from the uniformly accelerated, from uniform motion.
Right.
You notice radiation, and you would say, well, it might be that brief moment of uniform motion. You would say, well, something is wrong with my equations.
Well, again, look, the claim is once you settle back into inertial motion, the radiation will go away, right? There'll be no radiative phenomena. Now, you're right. There could be traces of earlier radiative phenomena. But again, even at the time when the radiation occurred, at the time of the acceleration, there's no question that there are observable effects of the acceleration, right? I'll know I'm accelerating. The claim, Galileo's claim is rather, once that's over and we just look at the phenomena being produced now in the new inertial motion, those phenomena will be the same as they were in the initial period. So I don't think we have any disagreement here. There's certainly no disagreement that the acceleration will produce observable effects. It's actually, look, what we're going to get to in the end of this is that this intermediate period of acceleration is really essential, right? It's essential for Galileo's example, because his example involves inertial motion, acceleration, end of acceleration, new inertial motion. And you could say, what do you mean new inertial motion? How do you know it's not the same as the old inertial motion? And the answer is, because I know I accelerated. Now, in the philosophical literature about this, this is, again, when I say there's a lot of controversy. I don't have it here. Some philosophers think, well, gee, that means a Galilean what Galilean relativity requires there be a third object or a second object, like the shore. So you say, what makes you think that the second time you run the experiments, you're in a different situation physically than the initial time. Right? Why not just say it's the very same situation? And some philosophers think, gee, that's right, in order for there to be any difference at all, the shore has to be there. So you say, oh, the difference is, and when I did it the first time, I had no relative motion with respect to the shore. And when I do it the second time, I now have a uniform relative motion with respect to the shore. And if the shore didn't exist, right, then I could make no distinction at all. So they think it can't be a global transformation. Galilean relativity can't apply to a global transformation. It has to be a transformation just of part of the world, and there has to be another piece relative to which you define the change from the initial state and the final state. Yeah.
Another example to think about inertial and non-inertial. Say you have an elevator in homogeneous gravitational field, okay?
Yep.
And you have a person in the elevator and a person outside.
Yep.
And the person in the elevator holds the charge, okay? And so it goes into free fall, inertial frame. So this charge stays there, doesn't radiate, it's static field. But for the observer from the outside, you accelerate, okay? And charge, being accelerated, it should radiate.
Mm-hmm.
Where is the paradox? Because this guy outside, you say, well, charge radiates, but this guy inside, inertial frame.
Right. I mean,
would say, well, no.
look, what you know is that if we're in general relativity, what we're going to say is that the free fall is the inertial state, right?
It would not radiate in general relativity.
Now, then your question should be, no, you see, the question is different. The question now is, suppose I take a charge here on Earth in a gravitational field and just stick it on the table. So according to general relativity, it is now accelerating, right? The unaccelerated motion would be the free fall motion if the table weren't holding it up. So really what your question ought to be is, if I stick a charge on the table, why doesn't it radiate? Because it's accelerated. No, it's exactly it's exactly your example, but let me answer it. It's because it's a linear. That's why you build a linear accelerator, because not every acceleration produced Bremsstrahlung. Right? That's why slack exists, and why it's harder to build to run CERN, because it's the angular change as the charge circulates that produces Bremsstrahlung, and that's why you build linear accelerators.
You are completely right. The question is why now the charge are
Right. And I think I just gave you the answer as well. Okay. So here's what now this is. Look, if what we think of as Galilean relativity is this phenomenology, and this is what I want to claim, this phenomenology, in a certain extent, we are going to be able to maintain in special relativity. We're going to be able to maintain it even in general relativity. But what is this phenomenology? It is the phenomenology of doing an experiment in inertial motion, accelerating the laboratory, stopping accelerating the laboratory, and then redoing the experiment. Okay? And that does not correspond to what we think of as a global boost. Okay? Because if I have a situation where everything's in inertial motion, and I do a global boost, in the boosted situation, everything's in inertial motion. Nothing ever accelerates, right? Global boosts don't produce accelerations. But Galileo's experiment, he doesn't talk about it, but to get from the first stage of the experiment to the second, it's essential that you have undergone an acceleration. Good. So what Galileo does is not a boost in the sense that I talked about, and in the sense most people would say a boost symmetry. Okay? That's not what Galileo talks about. And this is, so you're doing the same equipment, you're using the same equipment before and after you experience an acceleration. And absolutely, if you think of our original definition of a boost, the consideration of what the physical effects of accelerating a system are would never come into it. because the boost symmetry is going from one global situation to another, not by accelerating the first one into the second, just by transforming the global situation into a different global situation. Okay, so if we now think of Galileo's situation as like this. So before, these are my same two pictures, but remember before, this was a total global state of the universe. That was a different total global state of the universe. Now, these are two pieces of the same universe, right? So here's the situation where I run the experiments the first time. That's the later situation where I run the experiments the second time. These are both now in inertial motion, but the question marks represent physically what had to happen to get me from here to there, okay? There had to be a physical episode involving acceleration in order to get these spheres from this state of motion into that state of motion. And nothing about the Lorentz transformations, or nothing about what we call the Galilean transformations, will tell you anything about what goes into those question marks. In fact, what goes into that question marks is going to depend on the details of how I accelerated the laboratory, and the details of what's in the laboratory, and the details of the physics of what's in the laboratory. Okay? And no simple mathematical set of 4 equations is going to tell me that. Okay, so this is just what I'm saying. What determines the transition between the lower state and the upper state? It's the physics of the material and the details of the acceleration. That's going to tell me what the later state should look like given the earlier state. Galileo's assertion is that whatever that transition is physically that happened when he accelerated the ship from its initial state to its later state, whatever that transformation is, it yielded a later physical situation that was going to be empirically indistinguishable, that would give you the same phenomenology. Okay? And it need not be, and this is what we were talking about, it need not be, and in fact will not be indistinguishable during the transition. Right? You'll notice the acceleration when it's going on. Okay. Now, oh, sorry. So what does the physics have to be like to achieve that? What does the physics have to be like so that the effects of the acceleration yield a situation which is empirically indistinguishable afterwards? Now, Newton, after Corollary 5, which shows what we would call a Lorentz a Galilean transformation is a symmetry of his theory, he proves Corollary 6 in the Principia. So here's the statement of Corollary 6. He says, if bodies, anyhow moved among themselves, are urged in the direction of parallel lines by equal accelerative forces, they will all continue to move among themselves after the same manner as if they'd been urged by no such forces. So this is actually, again, this is Newton's statement of the empirical inaccessibility of uniform acceleration. So equal accelerative forces just mean forces that produce equal accelerations. This is the way we would have thought about the falling elevator, not in general relativity, where the falling elevator is undergoing inertial motion, but the way we would think about the falling elevator in Newtonian gravitational theory, where actually it's not an inertial system, everything's being accelerated, but equally accelerated because the gravitational acceleration force goes by the mass, and so that leaves us equal accelerative forces. Notice that the reason Newton needs this, of course, is that he wants to say that he can, for example, analyze how the moons of Jupiter go around Jupiter without worrying about the fact that the entire Jupiter system is in orbit around the sun, right? So the entire system is in fact accelerating, but essentially the accelerations are all equal. And so he can ignore them and just apply it as if, apply his theory as if the Jupiter were at rest. Okay, so you might say, look, if this is right, then here's one way for Newton to get me from the bottom situation to the top situation. Apply a uniform accelerative force over some period, okay, to all of my materials, and then turn it off. And afterwards, the stuff will now just continue on inertially. And if you could do it that way, notice, it's kind of interesting, if you could do it that way, then in fact, the phenomenology wouldn't even change under the acceleration, right? The fish would still swim around in the same way, and the water would drop in the same way, even under the acceleration, if it were done by uniform accelerative forces. Now, we know that's not the way ships actually work, right? They work that way when you drop them, but not when you speed them up, right? That's why you feel it when the ship speeds up. OK. So if this held, then you could fill in the gap between the lower state and the upper state with a situation with equal accelerative forces. So that would provide a transition. But notice, if you did that, the result would be what we call a Galilean transformation between the states, not a Lorentz transformation. So if you did that, you wouldn't, whatever you were doing, it couldn't be relativistic, right? Because essentially, analytically, what you would get is Galilean transformation rather than a Lorentz transformation. So you can't fill in between the two states that way in relativity. There's no the other way to put it is there's no relativistic version of corollary 6. Okay? There's a Newtonian version, but not a relativistic version. So the transformation between the initial state and the later state is going to be physically non-trivial. Okay, now, all of this leads me now to this rocket puzzle. So Bell, in this sort of lovely article, How to Teach Special Relativity, reports on having a discussion at CERN about an old puzzle. He didn't make it up. But he says he went into CERN, and we were just having a discussion over the following question. So I have two rockets pointed in the same direction, with projections coming out of them, and between the projections a thin thread has been tied fairly tautly. And at a signal which is emitted from the midpoint between the two rockets, so everything is initially at relative rest, and the rockets have been identically constructed, okay? So their space-time trajectories are going to be identical, right? They're going to have the same accelerations. So at a signal which is given out at the midpoint between the two rockets, when the signal gets to each rocket fires, and the two rockets fire and start to accelerate. Say, they go from here and they start moving this way faster and faster. And the question that Bell asks is a very straightforward physical question. Will the string break? Okay? And what he reports, I don't know if I have this here. So will the string, that's physics. Okay, there's a fact about what's going to happen. And what Bell reports was that most of the people he was talking to at lunch asserted very strongly it would not break. Okay? And that if Bell thought it would break, he didn't understand relativity. Now you can see why. Let's just stop for a minute and see how could people come it goes a little further. So the story goes, if you haven't read it, the story goes they argued about this. What Bell said was basically, look, no, there'll be a Lorentz contraction. Okay? The string will suffer a Lorentz contraction. It'll, as it were, try to tighten up, and since it can't, because the two ends are tied to these two rockets, eventually the tension will rise to a point where it'll overcome the tensile strength of the string, and the string will break. And his colleagues at CERN said, no, it won't break. And so they said, OK, let's go ask the theoretical division. I guess these are the experimentalists. So he said he did an informal poll of the theoretical division at CERN and asked them, will the string break? And he said the consensus opinion was, no, it will not break. Now, why would you think it wouldn't break? Well, here's a simple reason. Oh, you're just implementing a boost. An active boost and a passive boost are somehow fundamentally the same sort of thing. And one thing that cannot break a string is a passive boost, right? One thing that cannot happen is that because you change coordinates, you break a string, right? Changing coordinates is just a purely abstract.
I don't understand it. I really don't understand. single rocket. You have
When you say you don't understand, I'm not sure what you don't. I mean, all I've stated is I've retold an anecdote that Bell says.
one rocket inside.
Question, do you think the string will break?
No.
The string will break. Okay? So the string will break. Okay? It will. It will. This is Bell's point. In fact, the string will break.
There wouldn't be any then space travel because one single in the single rocket, you can have one rocket with two engines, okay, and then two engines, and then firing. And so, in other words, I mean, the rocket will just break into half. I really don't understand.
The string will break. I'll explain why. This is just a I mean, look, it's not. If you think it through however you like, clearly, sit down calmly and work through the calculation any way you like, you will convince yourself the string will break. I mean, the theoretical guys finally did a calculation, and they changed reference frames and did so and so, and they convinced themselves the spring would break. Bell's point was that you ought to be able to tell a story about the physics of this without changing frames of reference. You should be able to tell a story just as it were from the initial inertial frame of reference. In that frame, the rockets do not always maintain the same distance, right? Because they're exactly the same rockets. They have the same programming. Their trajectories through space-time are parallel. And the distance between the attachment points does not change. But the string does undergo an accelerative motion. And in fact, the physical effect of that accelerative motion will be to cause the string to tighten up, the tension in the string to increase to a point where eventually it will break. Let me just, yeah.
If you accelerate there, when you really have the relativity, but the string will be shorter in the direction of your acceleration, not perpendicular to
Right, but
and then the string perpendicular to the
no, it's in the same direction. No, that's not the situation. Here are the two rockets. The rockets are moving this way. No, one rocket is in front of the other. One rocket is in front of the other. They're both moving this way. The string is... Okay. No. They're one behind the other. One in front, one behind. Projections coming out the sides. String... Good. Okay. So look, I mean, look, this is just a physical... I mean, there's a physics of this. Right? And the correct physics is that the string will break. But they didn't realize. Now, you know, if you wanted, you could even add little rockets to each piece of the string, right? And that would be, when we asked about, so I said, look, there's no relativistic version of Newton's corollary 6. So I could add little tiny rockets to each little separate piece of the string and have them all be urged by equal accelerative forces. Okay? The string will still break. Right? Then it would fit Newton's condition. So, you know, just so it's clear, here are the rockets. They're pointed that way. The string is tied between a projection point here and a projection point here. So it's not a question of the rockets contracting or anything. It's just coming off the edge. The string is tied between, the thread is tied between it, and eventually, after a certain point, the thread will in fact break.
But another point, because in that point of view, when you have, the question is when you said at the same time we initiated,
Yes.
in which reference frame at the same
Right. I said in their initial inertial frame.
Yeah, because if you have some constantly moving inertial frame, you really need one rocket is faster than the other.
Yes.
And so the reference frame both
Yes.
at the same time.
That's right. In some reference frames, the one rocket will go first. In other reference frames, the back rocket will go first. Right?
You would say I started this rocket first and this one, and then it is normally that it breaks.
Right.
I started it first.
Right. But there's also a perfectly good frame in which the back one starts first. But you can do it the other way. There's a good reference frame in which the back one starts first. And you say, well, the string should go slack. Right? Then it should go slack if the back one starts first. And there's a good reference frame where that happens. Okay? Then the tightening of the string in that frame is so extreme that it overcomes the natural slackening you would expect and still breaks. I mean, one thing we know for sure, the string breaks. Right? It breaks in every reference frame. You can't change it from breaking to not breaking by changing reference frames. So what's the upshot of all this? Since Newton's corollary, this is what I just said, since corollary 6 leads to a Galilean transformation as a boost symmetry and the Lorentz transformation is not the Galilean transformation, the corollary 6 had better be broken by relativistic dynamics, right? It just doesn't obtain in relativistic dynamics. You can't get, in relativity, you can't get from the initial state to the later state by, as it were, constantly accelerating, uniformly accelerating all of the parts of your laboratory, the way you could for Newton. So what actually does happen, okay? In short, right, the particles in the string must not continue to move among themselves in the same way when accelerated as when unaccelerated if Galileo's phenomenology is to hold. That is, if after the acceleration I have a phenomenologically identical situation. All right, so what actually does get me from the initial state to the end state? Well, as Bell says, if I tell the story from the point of view of my initial inertial frame, I don't change the frame, I'm going to invoke the Lorentz-Fitzgerald contraction, right? I'm actually going to produce this, I'm going to invoke this and explain it as a physical effect, right? It's an effect that depends not just on space-time structure, but on the dynamics. It depends on the state of the physical body. So I have a thing I call a rigid solid. Now, not rigid, okay, it's rigid in what sense? In the sense that it has an equilibrium state. An equilibrium state that it will tend to return to after being subject to deforming forces, right? So this thing is rigid, not in the sense that it doesn't bend at all, but if I push down hard on it and it flexes down and I remove the force, it tends to return to an equilibrium state. That's what we mean by a rigid body. Solids are like that. Gases are not like that. Okay? Gases just don't have. So if the laboratory contains gases, then you have to have a different story. It's going to have to do with thermal equilibrium or something like that. So it's important that the laboratory contain, in this sense, rigid bodies. In order to get from my initial state to my Lorentz transform state, the rockets would have to be drawn together. So if I let those rockets fire, and then stop firing, and then go into inertial drift again, and I want the final state to be the Lorentz transform of the initial state, in that transformation, those rockets are going to have to be brought closer together than they would have been if they had just fired on their own. In fact, if instead of a thin thread, what I have is a very strong cable, okay? A really strong cable connecting these two rockets. Then as they accelerate, just as tension built up in the string that eventually breaks the string, tension will build up in the cable, but if the cable is strong enough, it will pull the backward rocket a bit ahead of where it would have been, and the forward rocket a bit behind where it would have been. Okay? It will draw them together relative to what their trajectories would have been without the cable in place. And then, when they stop firing and go back into inertial drift, they will be closer, right? In a straightforward sense, they will be closer to one another than had the cable not been there and contracted. Okay? The actual physics of the material of the cable, the tension in the cable, all of that played a role. So the question came up, it's gone now, why don't rockets fall apart? And the answer is rockets don't fall apart because they're made of solid material strong enough to produce countervailing forces that will keep things near this equilibrium point. And then if you stop firing, and of course, under the acceleration, the parts of the rocket will deform. And when you stop firing, it will tend to return to this equilibrium state. And the point is that the equilibrium state it returns to will be the Lorentz transform of the original state. It's because of that that when I run the experiments the second time, I get the same phenomenology. Okay? But the actual Lorentz transformation, an actual, in some sense, physical effect we can call a Lorentz contraction is essential to getting this result, the thing that actually corresponds to what Galileo describes. Same apparatus, 2 runs of the experiment with an intervening acceleration. Okay? So you have to think of the Lorentz contraction as a physical effect. It depends on the materials. And it depends on the nature of the equilibrium state, and it depends on the acceleration had better be mild. If the acceleration is too extreme, then the materials won't hold up to it. The string will break. It won't return to its equilibrium state. So what you can actually prove, and this is what Bell goes about proving just even for a single atom, is if the acceleration is mild enough that you will get these sort of contractive effects and time dilation effects as seen from the initial inertial frame. Okay? So that's what Bell shows, and it follows from that that the acceleration, if there weren't these interior forces, the end state after the acceleration wouldn't be the corresponding state, right? It wouldn't be the Lorentz transform state. And therefore, Galileo's phenomenology will not hold. For example, if the rockets are sending radar signals back and forth to each other and sort of timing when they come, if the cable breaks and the rockets are not drawn together, if the back one isn't pulled forward and the forward one pulled backward, then after the acceleration, the timing of these radar signals will change. They'll be different. Even after you've turned off the rockets and everything's gone back into inertial motion. So I guess this is what I just said. What's really doing all this is it's important that you have a solid, that the solid have an equilibrium state. And what you can show is that if the equilibrium state for a certain solid is such and such, then the equilibrium state of the Lorentz transform situation is the Lorentz transformation of the equilibrium state. And so it's going to, the attractor is going to attract you back into the appropriately Lorentz transform state. I mean, maybe that's too fact, but that's the physics of what's going on here. And therefore, if the experimental apparatus weren't solid in this sense, then the final state after the acceleration would depend sensitively on how the acceleration is carried out. And in general, you would not get what Lorentz calls a corresponding state after the acceleration. And therefore, the phenomenology need not be the same. Now, this is what happens in the Michelson-Morley experiment. There, the acceleration is not a linear acceleration. It's turning the apparatus. Remember, they had these interference bands. They tuned their apparatus to give them some interference bands when they sent the light different ways. And they had this whole apparatus on a piece of marble floating in a pool of mercury. And they would turn it, right? So that's an acceleration. And then they would stop turning it, okay? And then it would relax back into the equilibrium state. And what you would find is that the interference bands hadn't shifted. So that's the phenomenology, right? It's important that the apparatus was an elastic solid, and therefore, after you make the turn, after you make the acceleration, and you let it settle back, it's going to settle back and give you the same phenomenology again. The bands won't change. That actually does depend on what we've called a Lorentz-Fitzgerald contraction. That is, it depends on the physics interior to this marble slab and everything else, so that the effect of the acceleration will be wiped out by the subsequent return and relaxation to equilibrium.
Yeah, are you saying that this acceleration actually influenced the result of Michelson-Morley?
If you tried to, look, clearly if you tried to carry out the experiment while the thing was spinning.
Well, I'm talking about precisely the Michelson-Morley experiment.
Yes.
There was one rotation, right?
Yes.
Very slow.
Yes.
And then we have initial state,
Yes.
Final state,
Yes.
and no frequency shift.
Right. Correct.
So are you saying that this rotation has influenced the apparatus in such a way that there is no...
No, I'm saying the apparatus has responded, has reacted to the acceleration to return, and it's because the apparatus has a...
What was the consequence of this acceleration?
The consequence at the end, because the solidity of the apparatus returns it to the corresponding state, then the phenomenology doesn't change. If the apparatus didn't have that kind of resilience, which is produced by the interatomic forces, when you accelerate it, it could become displaced, right? The internal parts would be displaced. If they didn't return to the appropriate corresponding situation, then you wouldn't necessarily have the same phenomenology afterwards.
I cannot see this in correlation with this rocket problem and then this contraction of string or whatever it was.
Well, it's just, again, in order to get from the first state to the second state, you need an acceleration, right? I mean, you start out with one inertial condition. In some sense, you rerun the experiment in some sense in a different inertial condition, right? If you didn't change that, then you wouldn't expect any change anyway. In the case of Michelson-Morley, it's the rotational acceleration that takes you of the apparatus, right? You accelerate the apparatus by rotating it from one inertial situation to another.
So, but you can then ignore completely this acceleration, right?
You can because of the way the apparatus is built. Yeah, sure. Yeah. That's all I'm saying is it's important how the apparatus is built, that you can ignore it. Okay? If the apparatus were not an elastic solid, you couldn't ignore it. Right? The acceleration would have displaced things and they wouldn't necessarily return to the right situation afterwards.
You can say that they edit on some blade, right, which is also solid.
Yeah, yeah, right.
Do it very carefully.
Yes.
So that there is no.
Absolutely. Absolutely. Now, yeah.
Again, devil's advocate.
Okay.
What about energy balance? I mean, if you have, let's say, not a tiny string.
Yes.
Let's say very thick, 1 meter. Let's say.
Yeah, big cable. I talked about it when you were gone. Yeah.
To break it, you need lots of energy.
Yes.
Where it comes from?
The energy would come from the rocket engines. The energy that breaks it comes from the rocket engines. Now, if the rocket engines don't produce enough energy and don't break it, as I said, can I finish? If the rocket engines don't produce enough energy, that is, if the tensile strength of if we replace the string with a cable with a very strong tensile strength, the effect will not be that it breaks. The effect will be that the tension in the cable will pull the backward, the back rocket forward and the forward rocket backward.
Lorentz contraction and Lorentz transformation, because you are claiming that it will break because of the Lorentz transformation.
No, I didn't say the transformations don't break things. That's the point. It's because transformations don't break things that someone might conclude it can't break. But it does break. What I'm saying would break it is the effect of what I'm calling the Lorentz contraction. That's a physical effect inside the material, and it depends upon the physics of the material. It doesn't depend just on some abstract transformation. That's the argument. Okay, so we have to take account of the physics of the material. Should we call it a contraction? Okay, so here's something you might worry about, the word contraction. Maybe that's not the right word. We've shown that the internal dynamics of the string, that it breaks, or the cable, which would then deflect the rockets, or in the Michelson-Morley apparatus, when you rotate it, you have to take that dynamics into account when making the phenomenological predictions. Okay, that's just, you have to take account of the physics to make the predictions. In some frames of reference, the effects would be described as a contraction. So from the point of view of the initial inertial frame in the rocket case, the natural way to describe what's going on is to say, look, the rockets are not getting any further apart, right? The rockets maintain constant distance. The string breaks. Why did the string break? Well, the internal physics was trying to get it to contract, right? It was as if you had taken a cotton string and wet it, right, and let it dry out, and it sort of tightens up, and if it goes beyond tensile strength, it breaks, okay? So that's to call it a contraction, to call that dynamical effect of the internal physics of the material a contraction is the right word in that frame. Now, you might say, in some other frame, the word contraction might be misleading, right? The word contraction might not seem right in some other frame. And maybe that's correct. But in whatever frame you're dealing with, you've got to deal with the physics of the internal, you have to deal with the physics of the material. That's the point. And so in that sense, there really is a physical effect, which is what people sometimes complain that Fitzgerald and Lorentz thought there was a physical effect, but there isn't, because it's just a transformation, right? Without that physical effect, the Galilean phenomenology, which is that I get the same result after as before, wouldn't happen. Good. Okay. Yeah.
People doing solid-state physics said on this claim about this deformation. It should occur in some. I mean, there should be some evidence of this in some X-ray diffraction or something like that, right? Because it should be permanent. Right? I'm talking about this cable connecting these two rockets.
Well, it will be during the acceleration period. The tension will go up. I mean, that you don't need X-ray, right? I mean, the tension in the cable will go up. Whether the material exactly returns to its initial equilibrium state, you mean? There might be some fracturing.
You said that it wouldn't.
Well, if it does, it does. I mean, again, that depends. Sure. I mean, that's like asking if I press down on this and let go, does it really return to its initial?
It's elastic, right? But
yeah.
Then
Yeah, yeah, presumably there would be. Sure, there would be microscopic. I mean, I mean, it would depend on the material, but you would expect, yeah, maybe there are microscopic traces.
If you find some fine materials which
Yeah.
should
Yes.
show it, oh, it should be.
Yes, it should be there. It better be there. It has to be there.
Well, okay, but if you believe in this breaking, right? It's,
But it will break. It really will break.
about this change of state in internal state, which is just some kind of metaphysics, right?
Well, I don't know, but it's physics. The string break, look, strings breaking are physics, right? It's whatever string breaking is, it's not metaphysics. That's straightforward physics. A string breaks.
Anyone did this experiment, right?
Look,
Say X-ray diffraction material before, after, then you say then you have this distance between different crystal levels.
this might, so this is the, let me give you the kind of argument that convinced the theoretical people without doing the experiment. So we have these two rockets, they're accelerating, okay. Instead of telling the whole story from the initial inertial frame, go after a certain time and go into the instantaneous rest frame of one of the rockets, okay? And you'll find that in the instantaneous rest frame of one of the rockets are now further apart. And then you say, oh, okay, you know, in the instantaneous rest frame of the forward rocket, as it were, as I keep switching frames, the back rocket keeps falling further and further behind. And you say, of course the string will break. That's what convinced them.
Well, I'm talking about this change in material.
Yeah.
It's just kind of, claim which should be
Yes.
supported by experiment. My question is, do you really believe that solid state people would notice this?
Sure. Look, if this tension does not occur, if the tension in the string does not occur, relativity is wrong. All you're telling me is that the solid state people will tell me that that tension will leave microscopic traces. Fine. It'll leave microscopic traces. Even if it doesn't break, it'll leave microscopic traces. Sure. Okay, I mean, I don't know enough about solid state physics to say if it will or it won't. If the solid state people tell me that if I put my system under tension, that'll leave microscopic traces, then I believe them. And then you'd expect it in this case, because there certainly will be the tension. The issue is whether the tension is going to be there. And there certainly will be.
What about again, devil's advocate? What about, say, a hydrogen molecule?
Yes.
And you are difficult oriented in the right direction, it might be difficult, but let's say you have a dipolar molecule, let's say HF, okay?
Yeah.
You can polarize it in one direction.
Yes.
And you accelerate.
Yes. Yeah, because it'll get pulled together. That's what Bell shows. What will happen is that because of the interatomic forces, it will, looked at from the rest frame, those two things will actually get closer together. They'll be pulled together by the electromagnetic forces. That's just what Bell does by very careful calculation. Actually, he does it for a single electron orbital, and shows that the orbital will deform from a sphere into an ellipsoid. It will.
It will be HF molecule, but from the outside you have to transform your equations into relativistic form, and then you get these answers.
And from the point of view of the original frame, the actual molecules will contract. And the contraction will be produced by calculable electromagnetic forces in that frame. Okay, well, what does all this have to do with the constancy of the speed of light? This is the last thing I want to talk about. So I said, we have this other principle in relativity, the constancy of the speed of light, but then I worried, what do you mean by the speed of light? How do you calculate the speed of anything? We don't have a speed. Why does light have a speed? Okay, but just what we've observed about Galilean relativity, the proper Galilean relativity, the fact that the phenomenology of my experiment doesn't change if I do it in initial inertial motion, accelerate it, let it return to equilibrium, and then do the experiment in a new inertial motion, that the phenomenology doesn't change, that explains a lot about what you mean by saying the speed of light is constant. Now, I can explain this without talking about measuring the speed of light. People always talk about clocks and measuring rods, and I have to get speeds and numbers, but we don't need to do that. when we talk about the speed of light, whatever it is we're measuring, whatever experiment we're doing, it has to be sensitive to the trajectory of the light ray through space-time, right? That's whatever we mean by it. If any two things going along the same trajectory through space-time, they better have, quote, the same speed, okay? So we can set up an experiment that's sensitive to the trajectory of something through space-time that doesn't even attempt to quantify or measure or assign a speed. So here's an example. Suppose I have a light source. I have these rotating disks. I have slits cut into two disks. I have a screen. And this thing is spinning. I don't know how fast it's spinning. I don't have any meters, any measuring at all. I just know it's spinning. And one thing I can do is I just adjust the relative offset of these two slits to the point where the light gets through, right? At some offset, the light from the source will get through this slit and get through this slit and hit the screen. So without measuring anything, without assigning any numbers, without knowing any distances, without knowing any times, I adjust this apparatus so that what I can adjust is the relative orientation of the slits. I adjust it so that the light gets through. Okay? And now, having done that, I take that apparatus and I put it on a big turntable and I rotate it. Or I take that apparatus, I put it in a rocket, I accelerate the rocket, then turn off the engines and let it drift again. Okay? So I subject my apparatus to an acceleration, but then let it return to its equilibrium. What the argument I've just given you shows is that, again, if this is my initial state, and here's the light ray, and this represents a situation with the light ray managing to make it to the screen, it will settle back into the corresponding state, and in the corresponding state, the light ray will manage to make it to the screen. The phenomenology won't change. So to that, this is what Michelson and Morley didn't measure the speed of light. They were looking at interference fringes, right? They couldn't give you a speed from that. They were just looking for shifted in interference fringes. That's what they were looking at. And they see it didn't change when they rotated it. They wouldn't change if they took their apparatus, put it on a rocket, accelerated, and let it come back. All of that follows from what we've just shown. And so that's all you need to mean by the speed of light is constant. And I can say that without mentioning the speed of light, right? Without trying to measure the speed of light. It's a bunch of phenomenology that you would say that. So if we tune the machine, as I say, so that the light gets through, and then we linearly accelerate it, or we twist it, or whatever, let it return to equilibrium, the light ray will still go through. And so we do that in the first case with the source as part of the apparatus. But then we have, we've already shown that we'll get, that's the Galilean phenomenon. But then we have something else in addition to that. And now this is just the existence of a light cone structure. The other thing we know about light is that its trajectory is independent of the state of motion of the source, right? Because light rays just follow the light cones. Again, that's not a statement about the speed of anything. It's just a statement about how light behaves relative to space-time structure. So therefore, since I know I'll get the same result with the light source attached to the apparatus, I'll also get the same result if the light source is not attached to the apparatus. So all light will make it through the apparatus. And so in that sense, the speed of light will be constant, okay? Even though I accelerate my apparatus and so on. So that's really all we mean when we say the speed of light is constant. That's how you make sense of a claim like the speed of light is constant without attributing light a speed, okay? You make sense of it in terms of particular experimental situations and the outcomes, and a proof that the outcomes will be the same before and after the acceleration. Okay, so Galilean relativity, as I've defined it, plus the light cone structure, yields all the phenomena that we associate with what we call the constancy of the speed of light, even when no speed is assigned to light at all. And so that gets us to the end, finally. So unlike Newtonian physics, the phenomenon of Galilean relativity, as Galileo defined it, which depends on this intervening acceleration, actually does depend on dynamical features and the forces that make rigid bodies rigid. The internal forces create changes in the state of an accelerated body that can be reasonably called, I think, a Lorentz contraction. And so as a physical, you really need a Lorentz contraction as a physical effect is essential to explain the basic phenomenology of relativistic physics. Okay, that's the end. Took up all the time after that. Yeah.
We have just 5
Yeah.
minutes because
Yeah.
we have the only thing we have to respect is the
Yeah.
conference. All the rest is not.
Yeah.
So you will not have you cannot speak without the microphone. Okay. So you will everybody will ask and can speak only with the microphone.
Just
so
a short.
can I have the microphone?
Yeah, I'm sorry. I mean, well, we did spend some time taking questions along the way, so I hope.
Well, it's not important.
Hold on. You need the mic. It has to be recorded for posterity.
Well, it's not very important. The speed of light will be the same in that sense, but the frequency will change.
Yes, it will. Absolutely.
And that is observable.
Absolutely.
Okay.
That's absolutely correct.
Only what I wanted to say.
I completely agree. It's important that the frequency doesn't influence the speed, or else we wouldn't understand what we meant by the constancy of the speed of light. But you're absolutely right.
So if it's green light in your rope between 2 rockets,
Yeah.
and we get that speed of yours, I don't know, approximately of light, do I see the green light or violet light? Or?
No, this is just the point. The frequency of light will change.
Yes, but what color I see? If at the beginning was green,
Yeah.
what do I see now?
It depends. Which rocket? Are you in the
Yes.
forward rocket or the backward rocket?
No, in the rope.
But where are you looking at it from? To know what you
No,
see,
I'm in the rope, me and light.
you
and
and the light
change-
are in the rope.
Yeah, and it changed frequency. Let's say it was green in the beginning. What color is now? And
I don't know if you're traveling along with
And
rope.
do I see that
you're
color?
asking me a physical question I haven't thought about. My guess
No,
is it
am I
will continue.
seeing it
If
green?
you're sitting on the rope, it will continue to look green. That's my
yes.
guess.
So you were talking about the contraction
Yes.
at the end. So does that mean that 1 centimeter or 1 meter, which we measure in wavelength, is
It means the cable, if you want to talk about measurement, it means the cable, as it were, as measured in the initial rest frame, will literally become shorter. Okay?
I see the green light as green light.
Yes?
So the meter is again the meter because of the wavelength.
No, because you need, I don't know what you mean the meter. Yeah, as you travel along with it, any operation you use, assuming, well, now it gets a little tricky. Most operations you would use to measure the length of something, you would presume you're in essentially an inertial motion. Okay? I mean, think about spinning. So there's an acceleration. If I take sort of my normal laboratory operations and try and carry them out in a rotating laboratory, I wouldn't be too surprised if I got very different results. Okay? So normal laboratory operations tend to be designed essentially for things that are in a constant gravitational field in inertial motion. What this shows you is that any such operation, if you're in inertial motion, you'll get the same result. What will the effect of an acceleration be? Well, if it's a strong linear acceleration, that could mess up your equipment. Nobody'd be surprised about that, right? If you take your equipment and all of a sudden there are 18 g-forces on it, and you ask what the readout's going to be, and you ask me, is it going to be the same? Probably the answer is going to take a lot of analysis because most laboratory equipment is not designed to operate under stress, under that kind of stress. You would need a delicate analysis. If you're asking during the acceleration what you would see, this is the point. To ask what's going to happen during the acceleration, just looking at the Lorentz transformations, just looking at some simple set of coordinate transformations, right, 4 equations, that will not tell you. To ask what's going to happen physically under an acceleration, I need a very fine physical analysis of the materials, how it behaves under stress, what the relevant forces are, and so on. So I can't give you a straightforward answer to what the results of those experiments will be until you tell me a lot more details about what the experiments are, how they're carried out, and so on. And this is, as it were, at the root of, if we haven't been talking about quantum mechanics, any experiment is just a physical interaction, right? I mean, measurements physical interactions don't magically become measurements because we call them that. You have to do careful physical analysis of an experimental situation to see how it's going to work out. And typically, if I put things under high accelerations, they just won't work the same. But how they'll differ depends on exactly how they're made.
So I propose that we take a coffee and tea break, and we may continue in some form the discussion, either immediately now or in the afternoon, but we will decide that in the coffee break. So you are all invited in the library on the next floor, on the third floor, for a coffee break. Thank you very much.